Hello, this is Dr. Yamada. I'm going to show you molecular models, and some of them are very simple, some of them are more complicated. So this is my son, Theo. Um, Again, like H2 is a very simple molecule. The white represents hydrogen. So this is just H2. Okay, that's an overlap of a 1s orbital with a 1s orbital. And here we have HCl. Okay. So the green is generally chlorine. All right. Now, like we can't use s orbitals and p orbitals to make the bonds most molecules because they won't give you the right bond angles. So we have to use hybridized orbitals to make the bonds. Okay. So this sort of represents the tetrahedral hybridized orbital, sp3 hybridized, could be carbon, oxygen, or nitrogen. Okay, so this is the sp3 hybridized orbital. This is an example of an sp2 hybridized orbital, where the black represents the sp3 hybridized orbital. Remember, the sp3 hybridized orbital is trigonal planar, and the yellow represents the position of the p orbital, which is perpendicular to the plane of the hybridized orbital. Okay. Now, the sp hybridized orbital could be something like this. Let's say I'll use the purple. The purple will be the sp hybridized orbitals. So it's linear. Bond angle is 180 degrees. Remember, sp3 is 109.5. sp2 is 120. But sp is 180 degrees bond angle. So, and the red represents a p orbital going towards you and away from you. And the orange is perpendicular to that and also perpendicular to the hybridized orbital. Okay, so that's the orientation. Okay. So, okay. All right. Hmm. All right. Yeah. Maybe I destroyed it. Okay. Oh. Okay. So this is methane. Okay. So again, methane is a tetrahedral molecule. It has 4 bonds that want to be as far apart from one another as possible. This is AX4 type. Okay. So what we have here is we would have like the tetrahedral, the carbons sp3 hybridized. And so to make the CH bond, you have the hydrogen overlap here to make the CH bond. Okay, so that's how we get methane. So methane is completely symmetrical. So again, it's nonpolar. Carbon and hydrogens have about the same electronegativity. So anything that just has carbon and hydrogens in it is essentially nonpolar. Okay, we'll talk about that in a little bit. So This is, the green is chlorine. This is carbon tetrachloride. Okay, so this is completely symmetrical, so it's also nonpolar. But remember, the bond moment, chlorine is more electronegative. Okay. I'll move that. So, well, if we hold it up like this, okay, we have a bond moment going this way towards chlorine. We have another bond moment going this way towards chlorine. And those two will add to give you a bond moment going straight up. But we have two other bonds going slightly down. And they have a bond moment going down in one direction, down the other direction. When you add them, they will give you a bond moment going straight down. So the bond moment going straight up will cancel the one going straight down. So there will be no net bond moment. You can hold it like a tripod also. You have a bond moment going straight up. You have three bond moments going slightly down. When you add those three together, when you do a vector addition, if you haven't taken physics, or if you have taken physics, you should know something about vector addition, or if you've taken certain math courses. But if we have the three vectors going slightly down added, it'll give you a vector going straight down, and that will cancel the one going straight up. Okay, but the easiest thing is to use is that we have the most symmetrical. If it's symmetrical, it is nonpolar. Okay. Any questions? All right. So again, this is a molecular model of CO2. Okay, it's linear. It's completely symmetrical, so it would be nonpolar. Okay. Now we'll talk about how the bonds are being formed in a little bit. And this is an example of formaldehyde. It's an aldehyde. We have a carbonyl. It's trigonal planar. Okay. Bond angle is about 120 degrees, but it's not completely symmetrical, so this would be polar. Okay. So these represent a double bond, okay, in this case. Okay, it's not really showing you how the double bonds are being formed, but it just symbolizes the right bond angles. Okay. And this would be, we covered this in lecture. This is NO3 minus. Okay. So this is trigonal planar also, and it's completely symmetrical. And the blue represents nitrogen, the red represents oxygen. So this is nonpolar also. Okay. Now, here, this represents acetylene. Okay, we looked at this and we have a triple bond between the carbon atoms. Now, this doesn't show how the triple bond is actually being formed, but it does give you the right geometry. So this is completely symmetrical. Okay, now this is nonpolar. But if we replace the hydrogen with another atom, then this would have some polarity because it's not completely symmetrical now. Okay. So let's look at ethane. Okay. So this is ethane. Because we have free bond rotation around single bonds, this is a carbon-carbon single bond. We have free rotation. So all the hydrogens are the same. They're not any different. So if we replace any of these hydrogens with a bromine, we will only get one particular compound. Okay. So it doesn't matter where we replace one of the hydrogens. Orange is bromine usually. Replace one of the hydrogens with bromine, it doesn't matter where it goes. There's only one particular structure we can form. It doesn't matter if the bromine's here, 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 or here, because all the hydrogens were the same at the beginning. So it didn't matter which hydrogen we replaced to form this compound. Okay. If we add a carbon, though, let's see. If we make propane, okay, and you may need to make models to prove this to yourself, but when we make propane, not all the hydrogens are the same. And the same will go if we added another carbon, make butane, and so on. So these three hydrogens and these three hydrogens are the same. Okay, but the middle two hydrogens on the middle carbon are not, because this carbon's bonded to three hydrogens, this carbon's bonded to three hydrogens, and they're bonded to the same carbon. So these two methyl groups, CH3 groups, are the same. But this middle CH2 is different because it only has two hydrogens bonded to it. So these hydrogens are different from the methyl hydrogens. So if we take a bromine atom, doesn't matter where we place it on one of the N carbon, or we replace one of the hydrogens on the methyl group with bromine, we get this compound. Okay? And it doesn't matter where the bromine goes on those, as long as it replaces one of the 6 equivalent hydrogens, it is the same. However, if we put the bromine in the middle, then we would have a different compound. Okay. So this would be different. Now, if we take the middle hydrogen off, okay, we then have 2 methyl groups on the same carbon. This alkyl group here is called isopropyl, and I talked about that in the lecture. You guys need to know this nomenclature. We'll cover more of this as we go through other units. Okay. So if we take one of the N hydrogens off, and this group is called the N-propyl group. Okay. So where we have that. So if this is connected to something else, we would call that the N-propyl group. So if we put the bromine here, this will be N-propyl bromide. Okay, that would be a common name. We'll talk about IUPAC names later. So if we, and the one, when I had it attached to the isopropyl group, that would be isopropyl bromide. That would be a common name. Okay. Any questions? Okay. Now, okay. So again, this is methane. If we take one hydrogen away, all the hydrogens were the same, so it didn't matter. So this is called, we take one hydrogen away, this is called the methyl group. Okay, this would be the methyl group. And we have other groups as other alkyl groups as we'll discuss later. Okay. So remember, this was ethane, okay? And if we take one hydrogen away, then this would be the ethyl group. Because all the hydrogens were the same, so it didn't matter which hydrogen I took off to create the ethyl group. But when we have CH2, CH3, that's the ethyl group. Okay. So the methyl group can be symbolized as CH3, or it can be capital M, small e. The ethyl group can be CH3, CH2, or C2H5, because there's only one way to do that. Or we can use capital E, small t, to represent the ethyl group. Okay. Any questions? Okay. Now, when we have, let's go back to ethane. Let's look at how this sigma bond between the carbon atoms are being formed. Okay. So remember, those carbon atoms were sp3 hybridized. So we have a sp3 hybridized carbon overlapping hybridized orbital. That sigma bond is a overlap between sp3 hybridized orbital of one carbon with the sp3 hybridized orbital of the other carbon. So when they overlap, they have to have maximum overlap. Okay? They don't overlap like this or like this. They have to have maximum overlap. So the bond angles are still tetrahedral bond angles. Okay? So that's how it would form. So it's like taking this off and then connecting. So now we have this. We still have bond rotation because we don't have a pi bond. Okay. And the hydrogens will be out here, 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 and so on. Okay. Any questions? All right. Now, okay. Okay, this is a model of C2H4. This is ethene or ethylene. Okay, don't have to worry about the nomenclature yet. Okay, but this is a CC double bond, but there's no bond rotation. Okay, and you can't rotate around a multiple bond, at least not freely. Okay, so this is a older type of model using springs and sticks, but this is showing the same thing. Okay, so we have a double bond, and again, there's no bond rotation. Why isn't there any bond rotation? Remember, we talked about this. If you rotate the bond, then you will break the pi bond. Because the pi bond is formed usually by the overlap of p orbitals. So we can show that, okay, here we have a sp2 hybridized orbital and sp2 hybridized orbital. So the black are the sp2 hybridized orbital, and again, like any time you make the sigma bonds, you have to have maximum overlap. So they can overlap, but to make the pi bond, the p orbitals, which are the yellow represented, they also have to overlap to make the pi bond. That's why you can't rotate it, because then you would break the pi bond. And breaking the pi bond is too much energy at room temperature. So the compounds are fairly stable. Okay. So it needs to be like this. So that's why all the atoms have to lie in the same plane. So if you go back and look at this, the 4 hydrogens and the 2 carbons are in the same plane. This is a planar molecule. Okay. This is a planar molecule. Okay. So you can hold it like this, or you can hold it like this, showing you that it's a planar molecule. Okay. Any questions? Remember, we did another one with C3H4. It had a triple bond in it, the carbon-carbon triple bond. Or we did also C2H2, and that would be this in the molecular models. So we have a triple bond. Okay. So, and we also did C3H4, and we'll look at that one also. So for the triple bond, remember the p orbitals are the hybridized orbital. I mean, the purple is the hybridized orbital. So we have sp3 and sp3. So when we overlap this, the purples have to overlap to make the sigma bond, but then the 2 p orbitals also have to overlap. So the red will overlap to make one pi bond. That pi bond will be going towards you and away from you. And then the orange will form a pi bond above and below the plane. Okay, that will form the other pi bond. So the overlap of the 2 p orbitals will make the 2 pi bonds. So that's how we form the carbon-carbon triple bond, is 1 sigma and 2 pi's. Okay. Now, if we have the CH2 double bond to C double bond to CH2, that's the C3H4 one that we looked at in class. So the middle carbon's sp hybridized. So you would have this. But the other 2 are sp2 hybridized. So if we take an sp2 hybridized orbital, okay, so the purple and the black are the hybridized orbital, they have to overlap. So if they overlap like this, then the yellow has to overlap with the red to make the pi bond between these 2 carbons. Okay. But then when the other hybridized orbital comes in to make the other sigma bond, it can't come in like this because this p orbital has already been used to make this pi bond. So in order to make the other pi bond, it has to come in like this. Okay. So to overlap, so the yellow has to now overlap with the orange. Okay. So that means in this one, the hydrogens are in the vertical plane. In the other one, the hydrogens are in the horizontal plane. One's coming towards you, the other one's going away from you. So now all the atoms can be in the same plane. Okay. So this is the actual model of that compound. So not all the atoms can lie in the same plane. This is like above This is below in the plane of the board or paper. This one is coming out towards you. This one is away from you as you look at it. Okay, so they're not the same. Okay, but this compound is nonpolar because it's symmetrical, because it has a plane of symmetry. I guess it's better to look at it here. There's a plane of symmetry here. There's also a plane of symmetry here. So it's completely symmetrical. So this is nonpolar. Okay. But there's a special case. I think I showed you this in the other video. Okay. These two are mirror images. Okay, we'll show. But they're not the same. You can try to superimpose them, but you can't. These are what we call enantiomers. Things that are not superimposable on its mirror image. We'll cover this in a little bit more in chapter unit 4. And this is some concept that students have a hard time with. So things that are mirror images of each other but not superimposable, we call them chiral. Okay, and this is similar to your right and left hands. They're mirror images, but you can't superimpose them. Okay, so okay, I forgot to. I think I destroyed that molecule. So if we have a tetrahedral molecule and you have 4 different colors attached, if you were to make the mirror image of this, it wouldn't be superimposable. When we have a carbon generally connected to 4 different groups, it's what we call a chiral center. If we only have one chiral center, its mirror image would not be superimposable. Okay, and we'll talk more about this when we get to Unit 4. Okay. Okay. So, and this, what I was just talking about for the C3H4, this is showing you how the pi bonds have to form. And like this hydrogen is up, vertical plane up. This is down. This hydrogen would be down here. And this hydrogen is coming towards you. This hydrogen is going away from you. So they're not all in the same plane. So this makes one pi bond, and this overlap makes the other pi bond. So this is a representative of that compound. When we have CH2 doubly bonded to a C, which is doubly bonded to another CH2. Okay. Hope this gives you an idea of the three-dimensional structure of these compounds. Okay. Remember, there's no bond rotation. So I showed you this. This is like if we have C2H2Cl2, okay, the chlorines. So we have to have a pi bond. The U value is 1, and we don't have enough atoms to make a ring. this is what we would have. This is what we call the trans alkene. Okay. The hydrogens are on the opposite side, that's trans, or we can say that the chlorines are on opposite sides, so that would be E. Okay. And this is the cis isomer, or the Z isomer. So they're not the same. You can't superimpose them. And you can't turn one into the other because there's no bond rotation around the CC double bond. Okay. So that's what we have here. Now, we could make this into the geminal. Okay. But again, these two groups are the same. These two groups are the same. Remember, to have geometric isomers, these two groups have to be different from each other, and these two groups have to be different from each other. Okay, so in this case, we cannot have geometric isomers. Okay. That's the same reasoning when we look at, let's say, we have this molecule, okay, and all the hydrogens here are the same. So it doesn't matter if we replace one of these hydrogens with a methyl group. Okay. So if we have this, it doesn't matter if we rotate it like this, it's still the same. Turn it like this, it's still the same. Turning it like this is still the same. So there's only one structure that we can have like this. They're not any different. Okay. So again, because these two groups are the same, we don't have geometric isomers. You don't have cis or trans or E or Z. Okay, because these two are the same. Any questions? That's my son's hand. Okay. Okay. Hi. I just want to point out that this is like a ammonia molecule, NH3. And nitrogen is blue, the white is hydrogen. So this is AX3E. So it's tetrahedral structure, but it's pyramidal shape. Okay. So I just want to make sure you guys know that. I'll go over that. Like here we have AX3, trigonal planar. We also have AX2. This is linear. Okay. Now, if the blue and the red are different, then this will be a polar molecule. If they're the same, they're going to be nonpolar. Okay. So if AX3, if all the atoms are the same, it would be nonpolar. If all the atoms were not the same, then it will have some polarity. Now, if we take one atom away, then we have AX2E. So it's still trigonal planar structure because you have three things that want to be as far apart from one another as possible, but the shape will be bent and nonlinear. Bond angle is about 120 degrees still. Okay. So if we have, again, this is methane, but So we have 4 bonds that want to be as far apart from one another as possible. So that would be a tetrahedral structure and shape. This would be AX4. If we take one thing away, then one atom away. So we have 3 lone pairs and, one lone pair and 3 bonding atoms. So we still have 4 things that want to be as far apart from one another as possible. So the structure is still tetrahedral because you have 4 things that want to be as far apart from one another, but the shape is pyramid or trigonal pyramid or pyramidal. Okay. Now, if we have 2 bonding atoms and 2 lone pairs on the central atom, then this is AX2E2. So it's still tetrahedral structure because you have 4 things that want to be as far apart from one another as possible. But now the shape is bent, okay, or nonlinear. And again, the bond angles here is about 105 degrees. If we have AX3E, the bond angles are about 107 degrees. Again, if we have AX4, then it's 109.5 degrees. All right. So, and again, the basic rule of thumb is if it's completely symmetrical, it is nonpolar. If it's not completely symmetrical, it will have some polarity. All right. Now, okay, let's go back. Okay. So, okay. If we look at remember, water is AX2E, E2. So this is not showing you the lone pairs, but it shows you that water is bent or nonlinear in terms of its shape. Okay. So remember, this water is very polar. The OH bond is polar. Okay. So if we take like ethane and replace one of the hydrogens with an OH group, okay, and that was one of my sons. Okay, so this is what we call ethanol, CH3CH2OH. So remember, the CH part is nonpolar, okay, but the OH part is polar. So in this case, the OH part isn't, it makes a substantial portion of the molecule. So this molecule has polarity. It is considered to be polar. That's why ethyl alcohol is soluble in water. It's almost completely miscible with water. So this is a polar molecule. But if we add carbons to this, so if we add 4 more carbons, so we have something like this, okay. Wait. All right. Now, again, the OH group is the polar part, but the other part of the molecule, okay, return it. Now, most of the molecule now is nonpolar. Okay, only a small fraction is polar. So this is a model of what we call 1-hexanol or N-hexyl alcohol. And this is, we consider alcohols which has 6 carbons or more on it, and you only have one OH group in it. These are we would consider these to be nonpolar and considered to be insoluble in water. Okay. Any questions? All right. Now, the last thing I want to talk about, I think, is, again, when you have things that have a stronger intramolecular interaction, then it has a higher, let's say, boiling point and could have a higher melting point. But the melting point has more to do with its symmetry. So one of the things that determines boiling point is branching. Okay, so that's my son in the background. So this is N-pentane. Okay, we talked about this in lecture. So it's a straight chain. So if you had another one, it can go right over it. Okay, so this will have a lot of surface area with another molecule like itself in contact with one another. The greater the amount of surface area, the greater the interaction, the greater the London forces would be. So the greater the London forces, the higher the boiling point will be. Also, if we look at this, this is, we'll cover this in lecture, but these two CH3 groups are the same. So it doesn't matter if we replace one of these 6 hydrogens with a bromine or a chlorine or something else, then it would be the same molecule. Okay, but the 3 CH2s in between are not the same. They are this CH2 is the same as this CH2 because they're between a CH3 and a CH2. But the CH2 in the middle is different because these 2 hydrogens are different because this carbon is between 2 different CH2s. So in this case, the middle CH2 is different from the other CH2s. So in this molecule, you'll have 3 different types of hydrogens. So you can have 3 different monosubstituted N-pentane type of compounds. Okay, so just to point that out to you. And again, this may be hard to see on paper, but if you have models, I strongly suggest that you consider buying models. It will be more obvious to you if you have models. My son loves to climb on my back. Okay. Now, one of the other possible structural isomers of C5H12 is neopentane. Now, in neopentane, we have 4 methyl groups connected to a carbon. This only has one type of hydrogen. It's called, all the methyl groups are the same. Okay. So, but N-pentane has a lower boiling point because this is like a ball, makes like a sphere. Okay. So if we have another one of these nearby, there's not going to be a whole lot of surface area in contact. So this has less surface area in contact with another molecule. Therefore, this is like putting marbles in a container. And you can pour water, because the water will fill up the spaces between the marbles, because you don't have as much surface area involved. If you put like pasta, or I mean like spaghetti or noodles in a container, there's not much water you can add before it overflows, because there's a lot more surface area in contact. Again, the surface area in contact relates to how much um, um, is related to how much London forces you have. The greater the London forces, the higher the boiling point tends to be. So again, the more branching you have, assuming that the molar mass is about the same, then you have a lower boiling point. Branching lowers the boiling point, whether it's branching of the carbon chain or where the functional group is. All right. Any questions? All right. That's all for today. And okay, so next week we'll start Unit 2 and we'll discuss other experiments next week also. All right, you guys have a good one. Bye.